Hi, I am Kishor. You, Chen, and I are going to present our work with our advisors Sanjeev, Khanna, and Rajeev Alur on space efficient query evaluation over probabilistic event streams. A stream processing algorithm or a streaming algorithm works in this setting where there's a sequence of data points that arrive one after the other. These data points are processed as they arrive, and the state in the memory is updated. In the end, we are interested in evaluating a query over the entire input. In general, it may not be possible to store the entire input in memory, and hence streaming algorithms focus on space efficiency. In some cases, though, the data point received at a given time step might have some uncertainty. In this work, we try to model this uncertainty and provide algorithms for different class of queries in this model. Here are some of the previous works that consider modeling the uncertainty. These works either consider very specific queries such as min, max, and average as opposed to entire query classes like we consider in this work, or they do not analyze the fine-grained bit level complexity like we do in our paper. Here is a brief outline of the talk. We first introduce the streaming model, and then we provide algorithms for three different query classes, namely regular languages, queries represented using additive cost register automata, which is an automaton model with a finite state machine and a set of registers which are updated linearly. And then we have an automaton model with a counter which can be either incremented or decremented, but the decrements do not apply below 0. This is one form of nonlinearity that we consider in our paper. Finally, we conclude with some concluding remarks. As we saw before, a typical streaming algorithm looks like this. It receives the input AI, it updates the state of the system, and then waits for the next input. In the end, it returns the value of some query f evaluated on the entire input stream. The state the state used is required to be sublinear in the length of the input stream L and the size of the input set L. Typically, this is logarithmic in N and L. In our setting, we model events using a set of labels sigma. These events model can be used to model things like the data value being in a given interval. And at each time step, instead of getting a data point, what we get is a distribution over these labels. And then in the end, what we are interested in is computing the expected value of some query f evaluated on the sequence of labels sigma 1 to sigma n, where each sigma I is drawn independently from the distribution alpha I. We require that the state used be sublinear in the length of the input stream n and polynomial in the size of the label set sigma and the query f. Here is a simple example. The label set is given by the set of labels A and B, and the query is 1 if all labels are A's and then 0 otherwise. If the input stream is given by this sequence of vectors, where in each vector the first component denotes the probability of A and the second component denotes the probability of B, then the expected value of f is simply the product of the probabilities of A's, which in this case is 0.4 to the n. As you can see, storing this value in binary requires space linear in n. So in general, it might not be possible to output exact answers if we require the space to be sublinear in n, and hence we allow for approximation errors, but we also bound these errors uh, introduced by our algorithms. here is the notion of approximation that we will use. We say that U is an epsilon approximation of V if U lies within 1 minus epsilon times V and 1 plus epsilon times V. Let's look at the first class of queries, which is regular languages. For a regular language L subset of sigma star, we consider the query to be its characteristic function FL given by 1 if the word is in the language L and 0 otherwise. In this case, the expected value of FL is simply the probability that the string sigma 1 to sigma n is in the language L, where each sigma is drawn independently from the distribution alpha I. For this setting, we are able to prove this theorem, which says for a given DFA A accepting the language L, we can compute an epsilon approximation of the expected value of FL using space that is quadratic in log n over epsilon and almost linear in the size of the automaton A. How do we prove this? The algorithm is pretty straightforward. Here is a simple example. This automaton consists of two states. It accepts the language given by the set of all words where the number of A's is odd. As our state, we maintain a probability distribution over the set of states of the DFA, which is initialized to assign probability 1 to the initial state. On receiving an an input which is a distribution over the labels, we can update the probability of the states as follows. For example, the probability of ending up in state 0 is given by the probability of uh, being in state 0 and receiving a B, or being in state 1 and receiving an A. We can keep doing this, and in the end the sum of the probabilities of final states is the final answer. But as we saw before, we might need order and space to store these probabilities. Hence, instead of storing the actual probabilities, we only store the approximate bin it belongs to, where a bin is an interval from 1 minus delta to the x plus 1 to 1 minus delta to the x, where x is some positive integer. To do this, we need a couple of tools. What we show is that given a rational p, we can check if 1 minus delta to the x is less than p in order log x square space, and hence given a rational p, we can search for the bin that p belongs to in small amount of space. And then we also show that we can perform addition and multiplication using these bins. These operations do introduce some error each time they are performed, but what we show is that if we can choose delta sufficiently small, these errors, when they add up in the end, do not introduce a lot of error, and we do get an epsilon approximation in the end. Therefore, here is the overall algorithm. We choose delta based on the approximation factor epsilon, which typically looks like epsilon over the number of operations that we are going to perform. And then for each state, we maintain an integer xi, which indicates that the probability of the state I is roughly 1 minus delta to the xi. Now we use the operations on bins to update these probabilities, and in the end we output the probability of ending in a final state, and we show that the errors introduced by these operations uh, is bounded, and in the end we get an epsilon approximation of the final answer. So regular languages provides a class of queries that is that is either 0 or 1 on a given word. We would like to model more complex functions using automaton models. Uh, and the simplest of those is the additive cost register automata model, which has a finite set of states and a set of registers, in this example x1 and x2, and it has deterministic transitions, and on each transition the updates are given by linear equations. For example, in this automaton, if you are at state 0 and receive a b, you remain at state 0 and x1 and x2 are updated based on their previous values using the equations given below. And each state also has an output function, which is also a linear function of the registers. So given an input word, uh, we can follow this automaton, and then in the end, the state that we end up in, we use the output function of that state and the values of the registers to evaluate the function f on that word. For this example, f of w, the function represented by this automaton, is given by number of b's in w's multiplied by 2 raised to the number of b's in w if number of a's in w is odd and 0 otherwise. The algorithm for this model is very similar to the DFA case. First of all, we maintain a probability distribution over the set of states of the automaton as before. In addition to these probabilities, we also store these e values, where ei of x for a given state I and a register x is defined to be the expected value of the register x given that the current state is I multiplied by the probability that the current state is I. We can show that uh, we can update these e values using this equation, which looks complicated, but all that we need is that all operations in the update are either additions or multiplications. Therefore, we can use bins to approximate these e values as well. And in the end, the final expected value of f is simply sum over all states, the output function of that state applied to the e values corresponding to that state. And hence, finally, we get the following theorem, very similar to the DFA case, where given a additive cost register automaton A, we can compute an epsilon approximation of the expected value using space that is quadratic in log n over epsilon and almost linear in the size of the automaton A.
Up to this point, all models we considered are all linear models. So in the rest of the talk, we will focus on some nonlinear models. First, we consider the simplest model, which is counter with barrier. In counter with barrier model, there is only one state and one register, which we call the counter. There are only two characters A and B. Whenever we receive an A, the counter increases by 1, and whenever we receive the B, the counter decreases by 1. And there is a barrier at 0, so that if the counter has value 0 and receives a B, the value will still be 0. Note that the nonlinearity is only coming from the barrier. If the barrier is not there, the counter is additive, and so we can maintain its expectation in each step, as we shown in previous section. So it is natural to consider the connection between the counter with and without barrier. We prove that for any possible important sequence, the counter value without barrier minus the minimum counter value without barrier during the run. The picture is an explanation of this lemma. In the picture, the red line is the counter value without barrier during the run, and that high dashed line is the final value of the counter without barrier. And the lower dashed line is the minimum counter value without barrier during the run, and we claim that the counter value with barrier equals the difference between these two values. To see why this is true, we looked at the time when the counter value is minimum. We first observe that with the barrier, the counter value is 0 at this time. This is because that if the value is not 0, consider the last time the counter hits the value. The value at that time is smaller than the value at this time, even without barrier, since the counter never hit barrier during the time, which contradicts the minimality of the value at this time. Next, we observe that after this time, the counter will never hit the barrier again. This is again because of the minority of the value at this time. So, with the barrier, the final value is equal to the difference between the final value and the minimum value without barrier, which concludes the proof. Although the lemma is stated in terms of the deterministic stream, we prove that the situation is similar in the probabilistic stream. First, to help the explanation, we define some terms. Let xi be the counter value with barrier at time I, and xiu be the counter value without barrier at time I, and x minimum u be the minimum counter value without barrier. And note that by the lemma, xn equals to xnu minus x minimum u. Remember that counter without barrier is additive, so we can calculate the expected value exiu for every step. Each xiu is the sum of some random variables whose absolute value is at most 1. So by concentration bound, like Chernoff, each xiu is concentrated around its expectation, and thus the minimum value x minimum u is also close to the minimum expected value minimum exiu. Note that this is not the expectation of x minimum u. The minimum of expectation is easy to calculate. And so the counter value with barrier xi in each step is close to exiu minus minimum over exju over j smaller equal to I. With this, we are ready to describe the algorithm. First, we maintain the expectation of xiu minus the minimum over expectation of xju at each step. This can be done with very small amount of space, since counter with barrier is additive. We also maintain the probability that xi equals k for any k, which is close to exiu minus minimum over exju within a bandwidth of square root of n. Note that at each step, the value of exiu minus minimum over exju may change, so the values we are interested in are also changed. However, each time we only care about the probability at about square root of n values. We know that with high probability, the counter value with barrier is always within the range of values we have calculated. So in the end, we have covered almost all possible events. And the space complexity is about root n because we only maintain about square root of n values throughout all the time. So this concludes the simplest model. Next, we study a more generalized model, which is the counter with barrier in a DFA. In this model, the automata may have more than one state, but it still have only one register, which is the counter. Now, the increment and decrement are depending on not only the input, but also the state of the automata. For the example on the right picture, if the automata is in state 1, then receiving A will increase the counter, and receiving B will decrease the counter. But if the automata is in state 2, receiving A will decrease the counter, and receiving B will increase the counter. And in this model, we still have the barrier that keeps the counter value above 0. Let's first compare this model to the previous model and see what's same and what's different. First, the relationship between the counter value with and without barrier still holds. This is because this lemma holds for any possible sequence of increment and decrement. Also, counter value without barrier is still additive, and which means we can calculate the expected value exiu at all time steps. Remember that xiu is the value of the counter without barrier at time I. However, in this model, update operation is not only dependent on input, but also on the state. This means the update operations at different time steps no longer independent of each other, because the state at each time depends on the input of previous steps. And by this reason, we cannot use concentration bound and XIU may not be concentrated anymore. So if we want to use the previous algorithm, we might end up need to care about more than square root of n values. However, with a mild assumption, we can prove that the operations are almost independent. The assumption is there is a positive constant delta that, at any step, the probability of the symbol is at most 1 minus delta for both A and B. This is a reasonable assumption because in streaming model, the input in each step is normally independent of the stream length. So this assumption only says that at each step, the input has some uncertainty. However, the uncertainty is increased in an exponential manner over time. In fact, by a coupling argument, we can prove that the influence of the current state on the profile of the counter decreases as time passes. And after about log delta n steps, the influence almost disappears. And so that for any time I and j which is log delta n apart, the covariance of the operations at time I and j is small. And with this, we are able to set up a Doob martingale and use Azuma's inequality to prove that XIU is concentrated. This allows us to still use the previous algorithm in the simplest model and only maintain the probabilities of about square root of n numbers at all times. And this concludes the algorithm of the counter with barrier model in a DFA. In this work, we studied the model of probabilistic event streams and designed several space-efficient streaming algorithms for many classes of queries, which includes an automated model with conditional updates. We also proved a concentration result for random walk with barrier. For future direction, one may study the streaming algorithm for more expressive query classes in probabilistic streaming model. It is also interesting to establish tight lower bound results. For example, do we really need square root of n space for counter with barrier? Thanks for listening.